Section 8.1 is on the basics of a hypothesis testing. And the basic concepts of this refers to a hypothesis, and it's slightly different than a hypothesis written in, for example, a science classroom or a science lab or whatnot. It's a claim of statement about a property of a population, in our case. A hypothesis test, also referred to as a test of significance, is a procedure for testing a claim about a property of a population. Often a population parameter, population proportion, mean, or standard deviation, although I should probably know it can be other things as well, and we will be certainly looking at those from time to time. And they will be noted when they are indeed a hypothesis test. We need a way to determine, though, if a value is significantly high or significantly low, based upon what we're actually looking at, hence why they're in quotation marks. And the whole spiel for when it comes to this hypothesis testing is we have this flow chart here. So we first need to identify the claim to be tested and express it in some symbolic form, in the case of a null and alternative hypothesis. And the null hypothesis, well, we would first give symbolic form to these, give symbolic form that must be true when the original claim is false, and identify the null and alternative hypotheses, which is what this is doing up here. Alternative hypotheses is what denoted by H sub 1 is the one not containing an equality statement. So it uses a greater than, less than, or not equal to symbol. And the null hypothesis is the symbolic expression that the parameter equals the fixed value being considered. So null hypothesis is that the parameter, if it's spelled correctly, that is, parameter that's actually spelled correctly, not incorrect spelling of parameter, would be nice. So parameter would equal some number. For the alternative, we would have that parameter is greater than some number, less than some number, or not equal to some number, based upon the way that we're actually writing it. We would select the significance level, alpha, based on the seriousness of a type 1 error, and we'll be looking at what that actually is. You would make alpha small if the consequences of rejecting the true null hypothesis are very severe, such as in the medical field. Values of 0.05 and 0.01 are very common. You could also sometimes see a value of 0.10 as well. Those three are the common types, although 0.05 and 0.01 are the most common, since 0.10 starts going into the not too good category either. We would identify the test statistic for the test and determine its sampling distribution, so normal, t, and chi-squared for proportion, mean, and standard deviation / variance. The p-value method is the traditional method. This is the way that SAS will use to compute. We would find the value of the test statistic and the p-value, and then draw a graph and show the test statistic and p-value. Based on the p-value, we would make a decision. If it's less than or equal to alpha, we reject the null hypothesis. If it is greater than alpha, we fail to reject the null hypothesis. While using the critical value method, this is usually more usable when you are doing it by hand, although since p-values tend to be on the more skeptical side as it is, you could also use technology for this, but sometimes that could require a little extra work, unfortunately. But you would find the test statistic and critical values, or value, depending. You would draw the graph showing the test statistic, critical value or values, and critical region, based on if it's a greater than or less than or not equal to relationship. You would make a decision. If the test statistic is in the critical region, you reject the null hypothesis. If it's outside of the critical region, you fail to reject the null hypothesis. And based upon if you're rejecting or failing to reject the null hypothesis, you restate the previous decision in simple, non-technical terms and address the original claim. And the simple, non-technical terms is because, let's face it, for the most part, most of the people that be reading this are non-mathematicians, and specifically if we want the overall public to understand it, we would definitely not be using mathematical terminology. And let's face it, if you were to get a job in data science outside of the classroom, more often than not, you're going to have to explain whatever your results are in non-technical terms. And it should also be noted, based upon the decision-making note on this, we would never and if I could spell never correctly, that would be even more helpful in terms of this. But we never, ever, ever merely accept the null hypothesis. It's always in terms of either rejecting the null hypothesis or failing to reject the null hypothesis. So do bear that in mind. The confidence interval method specifically is an estimate of the population parameter about if it contains the likely values of the parameter. We will reject a claim that the population parameter has a value that is not included in the confidence interval, if we were to do it by this way. If we had a significance level for the hypothesis test of 0.01, the two-tailed test is 99% confident, one-tailed test is 98% confident. For a significance of 0.05, two-tailed test is 95%, one-tailed test is 90%. And for a hypothesis test of 0.10 significance, we would have a two-tailed test of 90% and one-tailed test is 80%. Do note how these values are different based upon this one-tailed test uses the alpha divided by 2 for the critical value, and in each tail of the two-tailed test, each tail is alpha divided by 2, so these are both tails. The hypothesis statements that we will be using, we have the null hypothesis H sub 0 or H naught. It is a statement that the value of the population parameter is equal to some claimed value. No change, status quo is equal to something. Equal, always equal. The alternative hypothesis, H sub 1, H sub A, H sub capital A, depending on which way you read it, a statement that the parameter has a value that is somehow different than the null hypothesis. For this chapter, the alternative hypothesis must use one of the following symbols: less than, greater than, or not equal to. Again, we have differences for some hypothesis tests, but that depends on which one we're actually using. But these are the three symbols that we'll be using for these hypothesis tests in this particular chapter and this part of the unit. It uses a significance level of alpha, the probability value used as the cutoff for determining when the sample evidence constitutes significant evidence against the null hypothesis. Specifically, the significance level of alpha is the probability of mistakenly rejecting the null hypothesis when it is indeed true. So, the significance level alpha is specifically the probability of rejecting the null hypothesis when the null hypothesis is true. Common choices are 5%, 1%, and 10%. The 5% and 10% are the most common of those two, but you could see any of those three, again, depending on the seriousness of a type 1 error. The summary of this test statistic requirements and sampling distributions are here. We've seen these with the confidence intervals. They're the same thing, but just written out here. For the proportion p, we would use a normal distribution. The requirements for the normality are n times p is greater than or equal to 5 and n times q is greater than or equal to 5. Q is 1 minus p. The test statistic is z is equal to p hat minus p divided by square root of p times q over n. For the mean mu, that uses a t distribution. If sigma is not known in normally distributed population, or sigma not known and sample size is at least 30. T would be equal to x bar minus mu divided by s divided by the square root of n. We could also use the normal distribution if sigma is known and it has a normal distribution, or sigma is known and the sample size is greater than 30. We would use z is equal to x bar minus mu divided by sigma divided by the square root of n. For the standard deviation sigma, or variance sigma squared, this would be chi squared. Chi squared. The strict requirement for this is it's normally distributed, and chi squared is n minus 1 times the sample variance, s squared, divided by sigma squared. The test statistic is a value used in making a decision about the null hypothesis. You would convert the sample statistic p hat, x bar, and s to a score z, t, and chi squared respectively, with the assumption that the null hypothesis is true. The critical region is based on whatever the test statistic is, and if whatever the hypothesis statement specifically is, if we're looking at greater than, less than, or not equal to. It's also referred to as the rejection region, and it's corresponding to all values of the test statistic that cause us to reject the null hypothesis. So for a one-tailed hypothesis with a greater than symbol, being a right-tailed test, the critical region is in the rightmost tail. For a one-tailed hypothesis with a less than is a left-tailed test, the critical region is in the left tail. So this one down here. And a two-tailed hypothesis test, this is a not equal to relationship. The critical region is in both extreme tails. The p-value method, we make a decision by comparing the p-value to the significance level, the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from the sample data, assuming that the null hypothesis is true. So you're assuming that the null hypothesis is true. You're finding the probability of getting the value of the test statistic that is at least as extreme as the test statistic obtained from the sample value. If the resulting p-value is too high, then that's considered normal in that case, and so we do not reject the null hypothesis. But if it's low, based on that significance level, then we would say that it is not normal for that to happen, and as such we would then reject the null hypothesis. But we would look at the type of test that we have, a left-tailed or a right-tailed test. And based upon that, we would have a p-value is equal to the area to the right of the test statistic, with the critical region here in green. Or if it's left-tailed, the p-value is the area to the left of the test statistic, again critical region in green. Is the test statistic to the right or left of center? If it's to the right, the p-value is twice the area to the right of the test statistic. Or if it's to the left of center, we would use the p-value is equal to twice the area to the left of the test statistic. So those two are when we have a not equal to relationship. And there's a little bit of a distrust with the p-value. and that comes from this Basic and Applied Social Psychology. The editors, Trafimau and Marx, they issued a p-value ban in their journal specifically. And their ideas are that p-values are an excuse for lower quality research and easy to pass. It's misleading and misinterpreted, since you're finding these, if it's greater than, less than, or not equal to beforehand, you have the sample data. You can very easily determine what it is before even running the hypothesis test. Very large samples could result in small p-values, despite little practical difference, right? And the practical difference is what causes it to be misleading and misinterpreted. You could be saying it's significant, but it has absolutely no difference, or has very little difference where the result is not really that great to begin with. It's helpful, though, to analyze the power as a part of an analysis, and it's better to consider other results, such as the confidence interval, simulation results, practical significance, design of the study, quality of the sample, type 1 and type 2 errors, and the replication of results. But if we look at, on the other hand, right, there are some places that that specifically look at the p-value. They look at the p-value, and they reject articles. They reject articles that are not significant. Meaning that the p-value is greater than alpha. So there are some journals that reject articles that are not significant. I don't have an example specifically of a journal that does that, but just be aware that's why sometimes you see research that all that they do is claim different things, but they never publish the ones that are not significant. The problem with doing that then is well, number one, you'll have people redoing that same exact experiment without realizing that it's already been done before, so just a waste of time. But you also have the idea then that despite the fact that it's not significant, it could still give valuable results, and as such, it should not be just rejected just because it's not significant in the idea of what significant specifically there means. Again, this is all why there's a distrust of the p-value, because some places just outright ban it, some use it as an arbitrary reason to deny an article and not even publish it. The critical value method is a traditional method, and it makes a decision by comparing the test statistic to the critical values. The critical value of values separates the critical region, where we reject the null hypothesis, from the values of the test statistic that do not lead to rejection of the null hypothesis. Again, this way is typically better if you're doing it by hand. You can also use technology with it, but sometimes you might have to do a little digging around to get all the values that you need. You make a decision to reject or fail to reject the null hypothesis. For the p-value method, if the p-value is less than or equal to alpha, we reject the null hypothesis. So if the p is low, the null must go. If p-value is greater than alpha, you fail to reject the null hypothesis. For the critical value method, if the test statistic is in the critical region, reject the null hypothesis. If the test statistic is not in the critical region, fail to reject the null hypothesis. We would write the conclusions based upon the fact that we never, ever, ever accept the null hypothesis. But if an original claim does not include equality, and I should probably note, in this particular section, the original claim does indeed include equality, so this first condition is not necessarily what we're going to be using, but we would see in later sections that this first condition is usable, but for the time being, if the original claim does not include equality and you reject the null hypothesis, then there is sufficient evidence to support the claim that, and whatever the original claim is. This is not a common test for the time being. And later on we will see where this is applicable. For the time being though, don't worry about this particular condition. For the original claim does not include equality, and you reject the null hypothesis, again, both of these are later, there is not sufficient evidence to support the claim that, the original claim. These last two are what this unit specifically is on. The original claim includes equality, and you reject the null hypothesis. There is sufficient evidence to warrant rejection of the claim that, the original claim, and the original claim includes equality, and you fail to reject the null hypothesis. There is not sufficient evidence to warrant rejection of the claim that, whatever the original claim is. For a confidence interval in hypothesis test, for a two-tail hypothesis test, we can construct a confidence interval with a confidence level of 1 minus alpha. And if it's a one-tail hypothesis test, we can construct a confidence interval with a confidence level of 1 minus 2 times alpha. A confidence interval estimate of a population parameter contains the likely values of that parameter. We should therefore reject the claim that the population parameter has a value that is not included in the confidence interval, hence where this comes from. But we may not always receive the same answer per se. For a proportion, the confidence interval is not equivalent to a hypothesis test, in the sense that they would not always lead to the same conclusion. For the mean, the confidence interval is equivalent, and they should lead to the same conclusion. The same thing for the standard deviation or variance. But for the proportion, though, it's not as clear-cut. For the type 1 or type 2 errors, type 1 error is the mistake of rejecting the null hypothesis when it is actually true, and alpha represents the probability of a type 1 error. So alpha is the probability of a type 1 error, probability of rejecting the null hypothesis when the null hypothesis is true, and the type 2 error is the mistake of failing to reject the null hypothesis when it is actually false. Beta represents the probability of a type 2 error. So this is beta, this was alpha. So beta is the probability of a type 2 error, the probability of failing to reject the null hypothesis when the null hypothesis is false. So the preliminary conclusion is we reject the null hypothesis. The type 1 error, though, is when we reject a true null hypothesis. So probability of type 1 error is alpha, and that's when the null hypothesis here, though, is indeed true. If the null hypothesis is false, that's a correct decision. If we fail to reject the null hypothesis, it's a correct decision if the null hypothesis is indeed true and we fail to reject it. But if we fail to reject the null hypothesis when the null hypothesis is false, that's the type 2 error. So fail to reject a false null hypothesis. The probability of type 2 error is beta. The mnemonic that we could use for this is routine for fun. Reject true null, so RTN, for type 1 error, and fail to reject false null, that's FRFN, for a type 2 error. That's what specifically the this specifically what are the constants of this particular statement. So this is this mnemonic device. Looking at the constants of this particular phrase. So, for example, consider the claim that the XSort gender selection method is effective in increasing the likelihood of a baby girl, so that the probability of a baby girl is greater than 0.5. Given the following null and alternative hypotheses, we want to write statements describing a type 1 error and type 2 error. So, null hypothesis, p is equal to 0.5. Alternative, p is greater than 0.5. So, for the first one here, we want the type 1 error. So, in order for us to do this, we have, in reality, p is equal to 0.5. But the sample evidence leads us to conclude that p is greater than 0.5. So the overall conclusion for this is the XSort gender selection method is effective. Is effective when in reality it has no effect. Meaning that we claim that it's effective since we claim that the proportion is greater than 0.5, but in reality it's equal to 0.5, so it has no actual effect. For the type 2 error, in reality, p is greater than 0.5, but we fail to support that conclusion. Meaning that we claimed that it was 0.5 to begin with. So we notice how we're not saying that we say p is equal to 0.5, we just fail to support that specifically. The overall idea structure then is the XSort gender selection method XSort gender selection method has no effect. Has no effect, that's what we claim, when it really is. It really is effective. It really is effective in increasing the likelihood of a baby girl. Okay. The power of a hypothesis test, specifically the probability 1 minus beta, of rejecting a false null hypothesis. It's computed by using a particular significance level of alpha and a particular value of the population parameter that is an alternative to the value assumed in the null hypothesis. A hypothesis test can have many different values of power depending on the particular values of the population parameter chosen as alternatives to the null hypothesis. Just as 5% is a common choice for a significance level, a power of at least 0.80 is a common requirement for determining that a hypothesis test is effective. Some statisticians argue that the power should be higher, such as 0.85 or 0.90. When designing an experiment, and of course that also depends on the seriousness as well, but when designing an experiment, we might consider how much of a difference between the claimed value of a parameter and its true value is an important amount of difference, and also the repercussions of said test as well. So let's consider the preliminary results for the XORT method of gender selection. There were 13 girls among the 14 babies born to couples using the XORT method. If we want to test the claim that the girls are more likely, p is greater than 0.5, with the XORT method, we have the following null and alternative hypotheses. The null hypothesis, p is equal to 0.5. Alternative, p is greater than 0.5. Let's use the significance level of alpha is equal to 0.05. In addition to all given test components, finding power requires that we select a particular value of p that is an alternative to the value assumed in the null hypothesis. So we'll use the alternative values of 0.6, 0.7, 0.8, and 0.9. So for this, let me build a table of those alternative values, the value of beta, and the power. And this just is going to show that we have those different values of the power. But for an alternative value of 0.6, beta is 0.82. So the power is 0.18. For an alternative of 0.7, the beta is 0.564, and the beta at the power is 0.436. For an alternative of 0.8, beta is 0.227, and the power is 0.773, and the alternative of 0.9, beta is 0.012, and the power is 0.988. Again, notice how there's different values of the power based upon the alternative, which influences beta, and in turn influences the power. Here is a statement similar to one in an article for the Journal of the American Medical Association. The trial design assumed that with a 5% significance level, 153 randomly selected subjects would be needed to achieve 80% power to detect a reduction in the coronary heart disease rate from 0.5 to 0.4. From that statement, we know the following. Before conducting the experiment, the researchers selected a significance level of 0.05 and a power of at least 0.80. The researchers decided that a reduction in the proportion of coronary heart disease from 0.5 to 0.4 is an important and clinically significant difference that they wanted to detect by correctly rejecting the false null hypothesis. Using a significance level of 0.05, power of 0.80, and the alternative proportion of 0.4, technology such as Minitab or SAS is used to find that the required minimum sample size is 153. The researchers can then proceed by obtaining a sample of at least 153 randomly selected subjects. Because of factors such as dropout rates, the researchers are likely to need somewhat more than 153 subjects. Thank you.